Hello students and welcome to the calculus course. In this video lecture we're gonna do one example from physics, but it consists of a few different tasks. And what do we have? What kind of example from physics do we have? We have this example. Weight is dropped. So we drop the weight, some object like a ball, from a fixed height, and let's give it a name. Let's say height h sub 0 when time is equal to 0. So we can write a formula for this process. So a formula for the height of the object at any point of time t can be written as follows. So how we can write the height? Height, which depends on time, so it's a function of time, is equal to h sub 0 minus g divided by 2 times t squared, where g, what is g? G is a gravitational constant. If you're in C system, it's going to be 9.8 meters per second squared. And if you're in a American system, it's going to be 32 feet per second squared. That's our gravitational constant. So let's fix some numbers for our purpose. So that h sub 0 will be equal to 50 meters. And this would imply that our height of the object will be 50 minus, and we're going to put 9.8 divided by 2 times t squared. And if we simplify it, we get 5 minus 4.9 t squared. 50 minus 4.9 t squared. That's our formula for this height at any time t. All right, so let's start by talking about average velocity. So what is the average velocity? Average velocity, and like if you suppose drive from New York to Boston, and you measure how long it took you to go there, then you take the change in your distance, so pretty much how far you have driven, and you divide by the change in time. And that would give you the average velocity. It will tell you on average how fast you've driven. So let's think about change in distance. Remember, for the change in something, we usually use delta symbol. So there's going to be change in h, so change in our height for the object divided by the change in time. All right. So basically, this tells you h2 minus h1 over t2 minus t1, right? So from the last class, it should be very similar to slope of a secant line connecting h1 t1 and h2 t2 from the previous exercise, right? All right, so what would be the first task? The first task would be find the average velocity average velocity between 2 points, between t sub 0 equal to 0 and t which is equal to 1 second. 1 second. All right, so let's try to do that. So for the average velocity, people usually put the numbers on the bottom, so it will happen between 0 and 1 on time, and usually people put a horizontal line on top just to say that it's average velocity, and this is delta h over delta t. So in our case, it's going to be h sub 1 minus h sub 0 over t sub 1 minus t sub 0, where h1 t1 is equal to, oh, sorry, wrong order. t1, that's the independent variable, and h1 is dependent variable, is given by 1, and then we need to find h1, we don't know it, and t sub 0, h sub 0, it's clear, it's going to be 0 and 50. 0 and 50. All right, so so we need to find h sub 1. So let's try to find h sub 1, which is h of 1, where h is our function defined over here. So maybe I should write it over here. H sub t is equal to 50 minus 4.9 t squared. 4.9 t squared. So let's try to calculate it. So we have 50 minus 4.9 times 1 squared, which is just 50 minus 4.9. 50 minus 4.9, which is 45.1. So we calculated h1, so we now know this quantity, so we're ready to finish this task. So we say equals. So h1 is 45.1 minus h sub 0, which is 50, divided by the difference in time, and the difference in time is 1 minus 0. So we subtract 45.1 and 50, we're gonna get, so we need to subtract 45.1 and 50 if you want to use a little calculator. So it's negative 4.9 divided by 1, which is negative 4.9 meters per second. That's our average velocity. So over the time of 1 second, the average velocity will be negative 4.9 meters per second. All right, so let's do second task. In second task, we need to find the average velocity between t equals to 1 and t equals to 2. So if we want to calculate the average velocity between 1 and 2, we have to take h of 2, subtract h of 1, and divide by t2 minus t1. All right, so h1 we know because t equals 1, so 1. So if we use t sub 1 and h sub 1, it's going to be 1 comma, what was it? Sorry, 45.1. 45.1, we already calculated this. And t2, h2 is equal to 2 comma, and this quantity we don't know, we have to figure it out. So to find h2, we have to calculate h of t2. So to calculate h of t2, we have to take 50 and subtract 4.9 times 2 squared, or 50 minus 4.9 times 4. So let's do this out. So we'll take 50 minus 4.9 times 4. So we're going to get 30.4. So 30.4. That's our H2. So we say equal, we say 30.4 minus 45.1 divided by 2 minus 1. So we need to calculate this quantity. So we have to take 30.4, we have to subtract 45.1 and divide by 1. So it's going to be negative 14.7. Negative 14.7 meters per second. Right, so again, this is the slope of a secant line. Slope of a secant line. Connecting these 2 points. All right, so let's change our task. Let's say we would like to know instantaneous velocity at t equals to 1. So basically, we have our parabola function, right? Parabola function. And our height is 50 initially, then it goes as a quadratic function, and eventually it will reach 0. So we'd like to know what happens at 1. So we'd like to know instantaneous velocity at 1. Before we did the secant line, like this, but what we want to find, the slope of the tangent line, in other words. All right. So, so let's try to do the same procedure as we did last time. So let t1 be equal to 1. We're going to make a small step to the right, which will be t2, and this distance over here, we're going to call delta t, change in time. Right, so let's try to set it up. So t1 is equal to 1. H of t1 is equal to h of 1, and we calculated before it was 45.1. And now t2 will be t1 plus delta t. Right, so it's going to be 1 plus delta t because t1 is equal to 1. So to find the instantaneous velocity is the same as finding the equation or the slope of a tangent line, right? The slope of a tangent line. So we're going to need h of t2. So it's going to be h of 1 plus delta t. So we take 1 plus delta t and we plug it into the h function. So it's going to be 50 minus 4.9 times 1 plus delta t quantity squared. So first we're going to simplify this expression inside. So it's going to be 50 minus 4.9. Then we use the not quadratic formula, but formula for the sum of squares. So it's going to be first one squared plus 2 times the first one times the second one plus second one squared. Again, this famous formula. And we're going to distribute 4.9 through the expression. So we say equal, we write 50 minus 4.9 minus 2 times 1 is 2 times 4.9 is 9.8 delta t minus 4.9 delta t quantity squared. Don't forget this minus, minus, and minus because of this minus. All right, we simplified this expression. Maybe we can combine these two terms together to do this extra step. So it's going to be 45.1 minus 9.8 delta t minus 4.9 delta t quantity squared. So now we're ready for our setup. So we say average velocity between 1 and 1 plus delta t is equal to h of t2 minus h of t1. Or maybe I'll do an extra step and write out what is the actual quantity here. So the actual quantity is h sub 2 minus h sub 1 over t2 minus t1. So on the bottom we get delta t, on the top we have h of t sub 2 minus h of t sub 1. And this is h of t sub 2, so we plug it in. So we're going to get 45.1 minus 9.8 delta t minus 4.9 delta t squared. On the bottom we have delta t, then we put this minus from here, and we have to write h sub 1, but we know h sub 1 was 45.1. 45.1. And like in the previous lecture, hint is the term at the end should go away. What do we mean by this? We have a positive 45.1 on front, and we have negative 45.1 at the end, so they add up to 0. So we say equal to, and we write negative 9.8 delta t minus 4.9 delta t quantity squared divided by delta t. And as before, we have to factor the common factor in the numerator. So we take delta t out. We're left with negative 9.8 minus 4.9 delta t divided by delta t. All right, so we have to justify that delta t we can divide in this expression. And remember, delta t was a tiny step to the right, so it wasn't 0. Conclusion, we are allowed to divide. So we divide it out. And what we're left with is negative 9.8 minus 4.9 delta t. And delta t is very, very, very small number. So what do we mean by very, 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 very small? Tiny step to the right in time. So like something like 0.00001. I don't know. Just very small number. But what happens if you take this very, 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 very small number and multiply it by 4.9? So if you take 4.9 and multiply by 0.000001, right? So let's try to do that. So if you take 4.9, which is this number over here, and you multiply it by 0.000001, your number is tiny, right? Your number is tiny. So this is your answer. So it's still small. Why I'm going into this discussion? Because I want to claim that this term over here is very, very, very close to 0. So it doesn't affect our 9.8. So since t is really, really, really small, t times any constant is really, 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 really small. So what can we say? We can say that the average velocity between 1 and 1 plus delta t is very close to negative 9.8. Very close to negative 9.8 meters per second. And why it's negative? Why velocity is negative in general here? Because the object is going down. So and our positive direction in the vertical space is up. So we got this part of the exercise, and there is one other part which will look very, very familiar to us, but let's still go through this. Part 4 of the exercise wants to go a little bit further. So part 4 tells us find the instantaneous velocity at any time t, for h of t equals 50 minus 4.9 t squared. All right. So basically what's going on, we have a timeline over here, t. You pick any point t that you want, right? And then you make a tiny step to the right. So you make a tiny step to the right, which is delta t, and this is going to be your t2. All right. So what would be our setup? T2 will be t plus delta t. H of t, we know it's this quantity, just 50 minus 4.9 t squared. We need to find h of t2, which is h of t plus delta t. We've done this procedure a couple of times. We take this quantity, we plug it in for t. So it's going to be 50 minus 4.9 t plus delta t quantity squared. So we simplify it like we did last time. So 4.9 t squared, 2 times t times delta t. Again, we use this formula all the time. Please memorize it. Plus delta t quantity squared. So we simplify it like last time. So we have negative 4.9 t squared, negative 9.8 t delta t, and negative 4.9 delta t quantity squared. Unfortunately, here we can't really simplify much. That's our equation for h of t2. So now we're going to find the average velocity between t and t plus delta t. So that means that's going to be h of t2 minus h of t divided by t2 minus t. So on the bottom we get delta t. In the numerator we get this expression for our h of t2. So we write it 50 minus 4.9 t squared minus 9.8 t delta t minus 4.9. Oh, I'll probably have to move to the next line because I don't think I will be able to fit everything in over here. So let me erase it. The line will be really, really long, so I don't think I will be able to fit things in. So equal, so let me move it over here so we have a bigger space. So we have 50 minus 4.9 t squared minus 9.8 t delta t minus 4.9 delta t squared. Then there is a minus from here. Now h of t, but what was h of t? H of t was this quantity, right? This is h of t. But since it's an expression, I have to use parentheses. Very crucial. So exclamation point, exclamation point, exclamation point. All right. So parentheses are crucial. If you don't use parentheses, there's a huge chance you're going to make a mistake. So usually conceptually we understand things really well, but we get confused in the details. And on the bottom we have delta t. So we set it up. Now we distribute this minus through the expression. So we have 50 minus 4.9 t squared minus 9.8 t delta t minus 4.9 delta t squared minus 50 plus 4.9 t squared, and that's the most mistakes this is where most mistakes are coming from. And on the bottom we have delta t. And the hint is after this minus, the terms should disappear. So let's try to see if it happens. This 50 is positive, this 50 is negative. We have negative 4.9 t squared, we have positive 4.9 t squared. So what can we say? We can say that, rewrite what's left. Negative 9.8 t delta t, negative 4.9 delta t quantity squared, delta t on the bottom. One more time, we have to factor delta t in the numerator. Negative 9.8 t is left, minus 4.9 delta t. And on the bottom, we have delta t. One more time, we have to do this justification. We'll do it for a while, actually. We are allowed to divide this delta t. Why? Because in order to find the average velocity, we have to make a tiny bit step to the right. All right, but then we're going to make our delta t so small that our average velocity is very close to the instantaneous velocity. That's our logic. So what's left? Negative 9.8 t minus 4.9 delta t. And delta t is very close to 0. Why it's very close to 0? Because it's a tiny step to the right. So what does it tell us? It tells us that this quantity is also very close to 0. Conclusion, our instantaneous velocity v is very, very close to negative 9.8 t. Negative 9.8 t. And it's any number t, so maybe I should have written it like this, function of t. Function of variable t. So you give me t, I'll tell you instantaneous velocity at time t. So the consequences. The consequences are finding velocity is pretty much the same as finding derivative of a function, right? Very similar procedure, and the velocity is just slope of a tangent line. What else? We don't have a mathematical procedure how to think of things that are close to something, and the question is how to remove this approximate symbol for the and replace it with an equal symbol. These are two connected things. First, figure out what it means to be close to something and what's going on, and then removing this approximation symbol and replacing it with an equality sign. So we'll start doing it from the next lecture, and I'll see you then.